IMFs, intermolecular forces, forces between particles, right. Alright, so while your computers are coming up, I want you guys to brainstorm right now on a piece of paper and then make this kind of like a bigger table with ionic, covalent, and metallic, and write down as many properties as you can think of, or compound identifications, anything you can think of. This is kind of serving as a quick review there, while yeah, you can do it as a table, but I think it's probably best for you to have it as your own reference, so make sure you write it on your own paper. Talk together. Talk together. Brainstorm session. Oh my God, who gave this to me? I can't remember who gave me this intro form. They didn't write the freaking name on it. Who came in there this morning?
Arushi, I know.
Is it Arushi?
I don't remember the
No.
Oh, the other kids.
What do they look like?
Dark hair. Right here.
Sean, thank you.
No, there's two types of
Oh. I see a lot of internet up. Good. Will you guys go ahead and log on to Socrative while we're, so if you don't remember, Socrative is just like it sounds, Socrative.com. Sounds it out. Good luck. Good luck. You good? Okay. You can leave your bag back in here too. I have bananas and apples and bagels and gum. Okay. Put it back. No, put it back there. So if they get there, just checking you guys in at that point.
Just London dispersion.
Huh? You can't. Well, I have to give you the student. Yeah, I'll tell you the student log in just a second. Okay. Alright guys, so I'm going to have you brainstorm and deliver some information to me as you can. So I'll start kind of in a round the world problem here. So Frank's table, you guys want to give me one idea about each one you found so far? Maybe one from each of you? Okay, so conductors in liquid form and what else form? What other form? And what? That's absolutely not in solid form, so that we're going to kick that one out. Aqueous. And aqueous form, good. I'm going to try to speak loud for my video here. Alright, and then Will, or Bradley? Okay, so we can say a polar molecule can exist, or a non-polar molecule can exist. And that's going to be something we'll elaborate on today a little bit more. And then Bradley?
The electrons in metallic compounds flow through.
Okay, what's the word we can use about used to describe flow? A sea of delocalized electrons, and that means to flow freely. Nice, good job, guys. Meredith's group. Anything you want to add here? Excuse me? Yeah, start with it. Start with one.
Alright, ionic, I said they had high melting points and high boiling points.
High melting points and high boiling points. Meredith? So did you say non-conductive?
Yeah.
Okay, so
Sorry.
covalents are non-conductive.
I
You're good. All right, so those are non-conductive in solution. We're just starting normal. Okay, thank you, darling. Let's go back to Jacob's group. High what? High melting points and boiling points as well. Good. Somebody else at your table? Keep going. Maybe what's the composition of these types of compounds? What's in them? Say again. Which one's metal, non-metal? Ionic. Okay, so many times our ionics can be a metal and a non-metal, or it can be two ions in general, right? Ions would be our ionic compound, just like our example from yesterday. What was our solid we put in our liquid solution yesterday? Ammonium, NH4. What was the rest of it? Nitrate, right? Ammonium nitrate. Well, do you see a metal there? Nitrogen, hydrogen, nitrogen, oxygen. No, those are all nonmetals. But thinking outside of this metal, nonmetal kind of really small category, we expand to just being inclusive to ions. And so that's ammonium ion and that's nitrate ion. So sometimes we do have to think outside the box there. Jacob, something from you? So we said ionics are metal, non-metal, or ions in general. Maybe contrast some of the others. Give me something. I'll come back to you in just a hot second, okay? Irie's table? Somebody here? In that lattice structure, it has just what as its composition? Like what's in it? This is not a trick question. Metals, okay, so lattice contains metal atoms. Something like that to indicate that you know it's just metals in that metallic structure. Somebody else from your table? Very soluble in water, right. So they're usually very soluble in water, and that's because water is polar and ions are going to be charged particles, and so they kind of attract to each other quite easily, and it rips them apart, and it makes them not only soluble, but when they're soluble and then they ionize, what can that cause that Frank said? Well, no, so once they're very soluble, meaning they're in aqueous solution, they ionize, they can cause the solutions to be, what'd you say? Conductive, right. So the ionic structure itself is not conductive. It's when they form ions in water and they can allow for an electrical current to pass through it, is it a conductive solution? Yeah, so it's actually more about the solution component at the end. Okay, so I got that. Let's go to the front table here. Anything you think of? I know we took a lot of them. Right, so this one's gonna be non-metal all the way. Non-metal, non-metal. Heck, even another non-metal. You can think of many things that have more than just two non-metals in them. For example, what is acetic acid? What? Maybe think about what does acetic sound like? Acetate. What's acetate? C2. 3. O2. C2H3O2 is acetate. So what's acetic acid? What acids always have H in the front. Boom. Acetic acid. Okay, and that's a 1 plus 1 minus. We're done. Now you see H's, C's, and O's. So that's why I said non-metal, non-metal, non-metal. It kind of doesn't matter. There can be many combinations there. So that's a good example there. What about the naming system with covalence? Let me add to that. What's so special about how we name covalents? So what do we call those? We can use prefixes in how we name those, like carbon dioxide, carbon monoxide, dinitrogen pentoxide. So we're using those prefixes quite a bit. In ionics, we don't use prefixes, point blank, right? Somebody else from this table. They're shiny and what? Shiny.
All students testing for AP US History,
And
please
malleable.
report to the check-in area at this time. Again, students testing for AP US World History, please go to the check-in point at this time. Thank you.
Okay, so there's a couple of things we can still contrast here. Okay, so the ductile, they're malleable. What about, so you guys mentioned the melting points here and here on ionic. What about covalent? Go for it. Right, they have low melting points and low boiling points, so they generally melt at maybe room temperature, or they're gases at, oh, sorry, speaking of that, they're actually gases at room temperature many times. So they're a gas at RT, room temperature, because they're so either nonpolar, they don't have high attractions for each other, so they start to disperse very easily and very quickly at lower temperatures. How would that differ between ionics? If these are gases or liquids at room temperature, who's a solid? Ionics for sure, yeah. So that's something we even mentioned yesterday, and I'm going to have to move this. This is all up in the way now. Okay, so this is going to be a solid at room temperature. What about metals? Except for who? Except for who? Mercury. Okay, so except Hg. Okay, so many times there are exceptions, and I don't always mention them, but we know that a blanket statement's not always the case. All right, I think we had a couple more properties we could speak of. Who is very, oh, let's go with you guys first. Yeah, Frank.
I would say that covalent is soluble in water also.
So it's a different way of speaking. So this is what I was hoping we'd get to today. Whoever puts like sugar to make into tea to make sweet tea, or sugar into coffee, or sugar into lemonade, right? We've all experienced that, right? And we know it dissolves. If not, we'd be like crunching on some sugar cubes or grains in our mouth. It'd just be disgusting. So we know it dissolves. But what does dissolve mean? Well, gases can disperse. That's not dissolving. Yeah.
It's like separate ions and they connect to the solution.
Okay, they interact with the solution or the solvent.
Yeah.
So you said ions, but what word does what type of compound does ion refer to? Ionic. When I say sugar, you're thinking. Does anybody know what sugar is? It's similar to glucose. The glucose is C6H12O6. Sugar is actually sucrose. Did you know that? Yeah. Okay, that's C11H22O. This is 11. This is 12. Okay. I'm pretty sure that's sucrose. Okay, so that's the formula of sucrose actually. Do you see ions there? No. So it cannot ionize. So that's why I want to stay away from the word ionize unless we're talking about ions or things that are ionic. So when I say the word dissolve, it's going to mean something different now.
Is it like the solvent, like surround or solute?
That's basically it. So dissolve doesn't mean, dissolve is a really poor term. It doesn't really give us any information. We just we know it kind of disappears. That's what we think about, right? But it means different things for different types of compounds. Dissolving here means that water surrounds the molecule. That's it. It's like basically a big sphere of water molecules surround it, and it stays in the middle. But nothing happens to it. It does not break apart. It does not ionize. It's still C12H22O11. But whenever you have, I'm going to put dissolve over here as well, it's going to mean something totally different. Whenever things like that are ionic dissolve, they actually do break apart, and they do what you said, Cassie. They will ionize and form ions in solution, and that acts very differently than a covalent compound does. Because when ions dissolve in solution, they're conductive. What's another word for a substance that when it dissolves in solution is conductive? Starts with an, say again? Electrolyte. And I think we spoke to this yesterday with Gatorade, right? Sweat. Okay. So this will form electrolytes in solution. So what about covalent compounds? What would you say they would form? Things that are non-conductive. Hydrate's going to be something different. Okay. So electrolytes are conductive in solution. So what are the things that are not non-electrolytes? You guys think I'm fancy? It's not fancy. We are not creative. So non-electrolytes. And I'm not really even talking about metals because let's think about it. Do metals dissolve in water? No, our spoon would come out with nub, right? If we were swirling our coffee, it would come out, well, there's a spoon, right? Because it would have dissolved. So these do not dissolve in solution, point blank. If not, all the bridges would be gone with the rain that's happening right now. So that's that kind of why I always stray away from talking about those much at all. Any other things, fun facts you can remember? Yeah.
With the sugar thing, like, it's like permanent coffee foam, and like if you put sugar, it doesn't dissolve.
Yes.
Like it's because of the heat, not the.
Right. So what happens is so sugar particles can still be clumped together. So let's call all of these sugar particles. Da-da-da. So we got like 5 or 6 little ninja. Okay, so we got all these sugar particles together. It's like sucrose. There are about 7 of them. So what happens when the kinetic energy is high, the water molecules kind of get in between them and starts kind of like pushing them apart. And those you can't taste. I mean, they taste sweet. They hit the sensors on your tongue and combine and then say, brain, you're tasting something sweet. But they don't crunch because they're so tiny. But cold water doesn't have enough kinetic energy, so nothing ever separated. So they're just bigger clumps, and so they start to taste crunchy, but you can still dissolve them in your mouth and they taste sweet. Okay, my demonstration work? Okay. All right, so let's go ahead and look at our water stuff real fast, and then we're going to move on, okay? So I'm going to show you guys this video while you guys have the other stuff pulled up. The video is going to have some water properties in it. You might want to write this down on your individual papers. Ready? Hold on. This is not the video. I know you will still love me the same. Okay, I'll stop. I am videoing. What'd you say?
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ion.
We were seeing that yesterday, and you had to draw that. Okay, you couldn't see it yesterday because it's like at the microscopic, nanoscopic, level that you can't see. But you definitely know that water, the Mickey Mouse thing, has 2 components of positive charge and negative charge. And so what's this red one supposed to be indicating? Oxygen, which has, why does it have this negative kind of feel to it? Because it has lone pairs on it. Those lone pairs are electrons, and they carry out a negative charge. And then these hydrogens, the gray ones, are indicating a more positive feel because they have a partial positive due to the lack of electrons, simply because it's got such a low electronegativity. Do you see how this kind of starts to bring back quite a bit of old information? And so you can see the interactions there. Now, what's happening here? Do not say dissolve. So what we would use for this type of compound? Ionizing. It is ionizing. The water is helping it ionize through this dissolution process.
This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. However, unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects aquatic organisms so that they can survive the winter.
All right, so you got enough information about water. I think you're prepared. Get on Socrative, okay? Socrative is going to be just a 5-questionnaire information gleaned from reading guides and from this video. You have your notes from your reading guide. One second, and you have your notes you just taken from the video. When you get on Socrative, get on computer, sorry, or get on a desktop. That might be faster. The internet is faster there. And then we're going to go through solutions a little bit more.
So are we using?
Yes, you were using the notes you just took. If you took notes and you're using the so I am going to review the water properties with you a little bit more formally. Not that you need it, but if you took your notes on your water video, might be information you can add to that. So, quick review. What IMFs hold water together? Specifically, hydrogen bonding. So that's going to be the most predominant IMF, intramolecular force, that's present within water. And that's because water is what? Polar, and water has, being polar, that's not enough for it to exhibit hydrogen bonding. Do you remember the characteristic about the polar molecule that showed you it was going to be able to hydrogen bond with another water molecule? Fawn. Okay, so tell me about the fawn. What do you mean?
Fluorine, oxygen, and nitrogen.
What do you mean, though?
Like it has to be bonded to hydrogen.
Yes, okay, H in the molecule has to be bonded to F, O, or N. So I have this water molecule. Is there a hydrogen bond here? Yes or no? No, none of these are hydrogen bonds. This is a covalent bond. This is a covalent bond. Those are not the hydrogen bonds. Okay? There's no, what have I not drawn yet? Another water molecule to show the intermolecular between water molecules. And I swear, people in my AP class still get that wrong, and I haunt them in their dreams nightly about this. Okay, so I'm going to draw this a little bit smaller so I can actually put you on the board. So remember, hydrogen bonding is not a bond. It's the fact that two water molecules can exist next to each other in a strongly attracted fashion due to their polarity and their the nature of their covalent bond. That nature of the covalent bond is simply, it is a super, super, super polar bond, because between O and H, O is more electronegative. Do you remember this? What is this? What's the right hand mean? Radius. Okay, so your atomic radius increases to the left and down, and then electronegativity, everything else is increasing in the opposite direction. Electronegativity, what's electronegativity mean? So if I'm fluorine, I am like literally the most electronegative element on the periodic table. If I'm fluorine, why am I so electronegative? I have 7 valence electrons.
You're electronegative, but you're attracting.
Right, so that fluorine, that 7 valence electrons is a group 7. It needs octet, right? So it's going to try to attract this another electron to become octet, to have 8 valence electrons. So oxygen, in this case, is very electronegative. And so not only does it have octet already, but it's actually these 2 electrons that are inside of this bond, they're being pushed or pulled towards oxygen. So in that, with respect to that, there's a very partial negative value here and a very partial positive kind of field there. And that attracts to this oxygen's partial negative due to its electronegativity and leaves our partial positives down here. So where's the hydrogen bond here?
Between the two.
So the dash line between the 2. Great. So just a quick reminder there. So boom, 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 boom. And basically you saw the properties that they've been listed about water. What were some of those properties? Adhesive, cohesive, what else? High surface tension, high specific heat capacity.
Substance and solid.
Yeah, and that's just weird how it arranges itself into a little hexagon shape. So all the properties about water depend on the fact that it has a very strong network of hydrogen bonding abilities. So there is a number of hydrogen bonding factors, and those are some of those characteristics that we basically relate back to the fact that it can hydrogen bond. You guys wrote down a lot of those. And then here's hydrogen bonds in, hydrogen bonds in action. You can see the dashed lines. See the water molecules kind of just floating around with interactions between the 2. So it's nice to kind of see that with another picture perspective. We talked about the surface tension, and they talked about how the surface of the water was the part we were referring to the most. So at the surface, there's water, hydrogen bonding to water, hydrogen bonding to water, hydrogen bonding to water. So it gives that strength of attraction, which means like water bugs can walk on it, right? Because it's not going to penetrate the surface tension. He's happy. It's Friday. Okay. And then it also gives it the ability to clump into like a spherical shape, because how does water come out of your shower? In what shape? Droplets. It's not like spraying you like a gas, right? It's in droplet form because of the surface tension it contains. This is the one factor they did not describe in the video, and this is something that's interesting for you to know about. It's basically showing the interaction between water, which is polar, and things that are not polar. Because we know eventually we can make them interact, right? You clean yourself daily. You wash the dirt and grime and oils that we naturally produce from our sebaceous gland off your face and your hands. But how? We're washing ourselves with water. Water's polar. Oil is non-polar. So we're forcing them to interact. Most of us, soap, okay? Most of us. My brother, when he was younger, would tell us he did. And we'd go in there and it was bone dry. He did not use soap. And then he told us he would brush his teeth and his toothbrush was dry. And I was like, no, you didn't brush your teeth. Oh, memories. Okay, so in case you didn't know, surfactant is a reagent, or it's a molecule that has one side that's super duper polar. It interacts really well with water, and the other side of the huge surfactant molecule is nonpolar. So it interacts really well with nonpolar things. So the surfactant is kind of like two-faced. It can interact with both types of compounds out in the world, and soap is a great example of that. And so soap and other detergents, like, laundry detergent, dish detergent, things like that, interact with 2 opposite things. And the reason why is because, I'm going to show you the molecule down here, is because of its elongated shape. But the purpose of doing that is that it allows for all the surface tension and the intramolecular forces and the hydrogen bonding to break apart so that they can start to intermingle. Because you can imagine, if you can't break apart water to water to water to water to water, water is never going to interact with oil. So you kind of have to separate the water itself first to actually begin that. So it interferes with the hydrogen bonding process. So here's your oil. So there's your oil molecule. And then this big zigzag thing here with the sulfate on the end is our surfactant. And then there's our water over there. So water's what are the white things here on water? Hydrogen, and you can see that partial positive from the hydrogens interacting with the tiny negative. Do you see the negative on sulfate there? It's little, but it's there. Okay, so they're interacting. So that's the polar end of the surfactant molecule. And then these long chains are actually carbon, 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 carbon. So chemists get really lazy, and instead of writing out carbons like that, they write it like this, and they go, yeah, every point is a carbon. So seeing all those carbons here, here, and here, those are all nonpolar, because there's no polarity difference. So they interact really well with the oil. Hence, it attaches on to the left to the oil, and attaches to the right to the water, and they go down the drain together, happily ever after. Yeah.
The surfactants are like nonpolar.
The surfactants are both. So since they're so large, they actually have one. That's nonpolar, which is, you can see this half over here, and then the other half is polar, which is this half over here. It actually is both. Yeah.
So what's the name of that surfactant?
That is a triglyceride. You know, like fats, triglyceride. It actually has, this is the triglyceride, whereas this is the sulfate component. That's just, it's soap. It's some sort of soap, which is, I don't have the name off the top of my head of that one in particular. But the triglyceride aspect is the glycerin molecules in the backside.
And why do you need water to work if the water isn't actually touching?
Because water is a great solvent of other things, so it actually allows everything to kind of flow together. So it's more of the effect of afterwards cleaning, like washing things away. Okay. All right, and that's it for chapter 15. Chapter 15 is super short, and I have jokes for you. I'm sorry, we just can't be together. Is it because I'm fat? Okay. And then I do love my jokes. Okay. Sorry, I just thought a joke would break the tension. Yeah? Yeah? That's all I was thinking. And then, help! Help, I'm dissolving! The beers are insoluble. That's easy for you to say. You're not polar. It's the symbol, okay? And then name's Bond. Hydrogen Bond. I don't have the rest of it for you. Okay, so that's it. Let's look at our Pogel stuff for a moment. So you guys took some time to look through this. This is me introducing solubility to you through data, and then we'll look at graphs, and then we'll actually figure out what this actually means. Okay. So we know solute and solvent interact to make a what? Solution. And you can see that as you probably have done this to yourself. You put too much sugar in your coffee, or in sweet tea, or in some sort of cold coffee, and does it always all dissolve? No, it doesn't always all dissolve. So eventually it comes to the point where it has met capacity. All of the sugar or all the substance that's going to dissolve is done dissolving. At what point did we meet that on this first experiment? Where? So between trial 3 and trial 4, basically when you is kind of what you're fighting with yourself on. I'll say you can definitely see the capacity of our 10 gram solution was 3.6 grams of said solute, right? So we met that once we started adding 4 grams. At the 3 gram aspect, have we met capacity? No. I can add upwards of, I can add 3.6 grams total. So when I only added 3 grams dissolved. But could I have dissolved more in that solution? Certainly. Okay. There are some words that we use to describe solutions. The 3 terms can be, and you guys are going to tell me which one would apply here. Saturated, unsaturated, and supersaturated. Okay? And to give you some inspiration before my favorite video of all time.
What's about to dissolve? We saw you.
This is great. Now we're going to get sued by ACDs.
The salt dissolved in water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, the same throughout. Homogeneous, the same throughout. Solvents that are polar can dissolve solutes that are polar or ionic. That is really cute. Water and nonpolar solutes just won't mix, but a nonpolar solvent like an E can fix. Like dissolves light, polar and polar. Like dissolves light, nonpolar and nonpolar, and all the solvent molecules.
You saw that, right?
Yeah.
We have seen this before.
Yeah.
Okay. Just making sure you know this is my favorite one.
Use smells better stuck to the solute ions in your cup. Solution saturated in its full form. Sure, solubility's been reached for that temperature. Saturation on the line. Saturation on the line. If you spill some water molecules unstuck, then most likely can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated. Put more in. Unsaturated. Put more in. If you put more solute in, then can be dissolved. Then a supersaturation situation's involved. The antis falls out as a precipitate. Or the solution is unstable, so you acetate. Supersaturation. Precipitate. Supersaturation. Precipitate. A salt.
Okay, so they basically said unsaturated meant what? You had room to add more solute to your solvent, meaning it just wasn't saturated yet. Supersaturated was what?
Too much.
There was too much in there. It caused it to be unstable. It precipitated. Another way to say that is just not all of it dissolves. I will show you a solution like that, I hope, shortly. Okay, so here, back here, on the experiment 2, when did we meet saturation? Okay, so what is the saturation point of solution 2? 7.2 grams, right? Hold on. There it is. Okay. So 7.2 is the saturation. When did we meet that? Basically trial 8, because you can't say trial 7 because it's what at that point? Unsaturated. And then trial 3? Or experiment 3? 18 grams, you're right, is the what? That's the saturation point. And when did we meet that? Trial 6, yes. And this was over here at trial. Are we good? Yeah. All right, so you're starting to see how the data can give you information. But what the heck is solubility? Yes, question.
All the other ones are really, oh, because it's 18 now. Okay,
Yeah, it happens to be the same. All right, so solubility is, as you guys read on the, or saturation, as you read on the introduction, was basically you saying how much solute could dissolve in a given amount of solvent. And our idea here was that we were looking at grams of water, grams of water, grams of water. Let me actually pull that question individually. Well, it's actually in the next section. Where it said read this, solubility is a measure of, let me pull that up for you guys. Where it says read this, solubility is a measure of the maximum amount of solute that can dissolve in a given amount of solvent at a specific temperature. Notice that graph that was on the video, it was like at this temperature. So it is pretty temperature dependent. In other words, it is the ratio of the solute to solvent in a saturated solution at a specific temperature. Solubility is typically generally related per 100 grams of water. For example, if you have, from our data, you can see something different, but if you have 20.4 grams of sugar that will dissolve in 10 grams of water, we can actually make a ratio. What is that ratio? Any takers? It's just like a fraction. So it's nothing crazy. You're going to take your 20.4 grams of sugar, and that will dissolve in what? What did it say? 10 grams of water. Okay? So, using the same ratio, how much would you say, and you can see their example here, would dissolve in 100 grams of water? Why that much more? Because you multiply by 10, because this is supposed to be resembling a proportion. It is proportional, it's a ratio. So if 20.4 grams dissolves in 10 grams of water, you could figure out in 100 grams of water how much dissolved. You see it's a proportion? So how would I solve for that? Cross multiply and divide, or you can see it's a ratio of 10, or a multiple of 10 greater, so 10 to 100, 10 times greater. 20.4 to that would be 10 times greater as well, so that x would be 204 grams. Yeah? 204 grams. So that's what we're looking at, is proportions and ratios. So if I have an ocean full of water, I can dissolve a lot. If I have 10 grams of water, I can't dissolve as much, but it's still proportional. Question?
When would you use like the percent by volume and percent by mass?
We will talk about that shortly. That's usually a volume to volume ratio. We're talking about grams to gram ratio. We can do gram to gram ratio by percentages. So the question was, and you guys maybe even seen this, who's ever seen like in the drugstore or CVS or Walmart or whatever, 3% solution of hydrogen peroxide. or 10% or 97% isopropyl alcohol. There's all these percents, and it's because most of the population can't do this, but we're like, yeah, that's like 97% isopropyl alcohol. That's mostly alcohol, right? Or 3% hydrogen peroxide. That's like basically water, right? It's in solution. But it's very little of the hydrogen peroxide. Hydrogen peroxide will burn you if it's too concentrated. So they put it in percents because most people understand percent, because they can get it sort of like, oh, it's 20% off. Like they understand how to recognize that. We're the educated population. Okay, so looking back at the data, and you may not need to, you may need your partner to sit next to you, but would it be acceptable for information here for trial 2 from experiment 1 to determine solubility? Hold on. Let's not do that one. This is the one I want to do. All right, so in model 1, none of the experiments were identified as 100 grams of solution, but you saw 10, 20, and 50. Let's determine, based on the data, the saturated point of each of these. So I'm going to do this on the board over here. You guys should write this down on your own. This is basically question 8 underneath this section. So what was the saturation point in experiment 1? 3.6 grams in what? 3.6 grams in 10 grams of water, right? All right, what was the saturation point in experiment 2? How much dissolved? 7.2 grams in what? 20 grams of water, and you can see that was different for the experiments above. The last one? 18 grams in what? 18 grams in 50 grams of water. Okay, so this is all the same substance, right? All the same solute, all the same solvent. At what temperature? Didn't it say 20 degrees Celsius? So these are all at 20 degrees Celsius. So we're not changing any of their variables except for what? The amount of solvent, 10, 20, 50, and because of that, the solute will be saturated at different grammage here. So let's go ahead and convert this to what it would be in 100 grams. You may be able to do that very quickly, but you're setting up a proportion. 100 grams of water compared to the 10 grams of water should dissolve how much more? 10 times more. So how much should be dissolved in 100 grams? 36 grams. Okay? Same thing here. If I want to put it into 100 grams of water as a ratio, 20 grams goes into 100 grams how many times? 5 times greater. Okay, so what would this be? Say again? 36. Why?
Because 7.2 times 5 is 36.
Right, so 7 times 5 is what? 35, and then 0.2 times 5 is 1, so that's 36 again, right? Huh. 36 grams per 100 grams, 36 grams per 100 grams. Looking good so far. What about this one? So 50 times 2 is 100 grams of water. What about this one? 36. So what is the saturation point of this substance? 36 grams per 100 grams. And it doesn't matter that I put it into different solvents, different amounts of solvent. If when I get them on the same playing field, which is 100 grams of water, which is always how we define solubility, it is the same thing because it's at the same temperature, so it should be. You're not, and as we're using the same solute, you're going to see that as well. Questions there so far, guys? Cool. Okay, so I'm going to come back to the solubility curve aspect of that. So speaking of solubility, you can kind of intermingle this with your Hegel notes that you've been taking. I just got to keep an eye on the time. Make sure that you write down for yourself that it's important to use, at least identify the temperature of our solution, because the temperature is going to drive how much actually can be dissolved in a given sample. So of course, something really hot, like hot coffee, it would probably dissolve a lot more sugar than cold coffee, and that's kind of the kinetic energy aspect. But for us to actually do a comparison, we always try to deliver it in the same units as grams of solute per 100 grams of solvent. Gases are different, so make sure that you do include that small fact as well. It's because gases are so, they fuse very easily, they're very spread out, they're not as compacted as a solid. We generally use that as grams per liter versus grams of solvent. And you saw some of the diagrams as the picture or as the little video is being shown with the saturated aspect of the solution. It means it's at capacity. That means no more solute will dissolve. And as no more solute dissolves, there is this interplay between the solvent and solute interacting, but we call it dynamic equilibrium because in the exchange that is occurring, can I scroll down a little bit? A little bit? Okay. Okay. So in the exchange that's happening here, as the water molecules are coming in and like attacking the solutes, it starts to get ripped apart. And it's only going to do that until it is saturated, until it's at capacity. But you can still have ions find other ions, and many times ions will interact with each other and they'll attract and they'll maybe even form a solid once again. So you can have a positive ion and a negative ion come back to make its ionic compound, but immediately the water will attack it and it will dissolve. So it's still a dynamic process. The solute's not just sitting there doing nothing. They still interact with water, they still interact with each other. And so since it's dynamic equilibrium, we'll have this constant exchange back and forth between dissolved, undissolved, dissolved, undissolved, dissolved, undissolved. But it's still at capacity, it can't dissolve anymore. Give me a thumbs up when you're good here. You can see some of the pictures here that are supposed to be indicating that to you. Well, how it's switching. A video, like something in motion, would be so much easier to show you that. I'll do a little diagram here. So it's almost like actually right here as it is. So these two diagrams kind of tell the whole story. As the solute, which is here, the lattice structure, goes into solution, water starts to attack it. And as water attacks it, it dissolves into cations and anions. They'll hang out, they'll stay out away from each other, but then occasionally a cation and an anion can come back together, and they can come back together and reform some of the solid. But it's so tiny and minute you can't see it, because then it would be like a solid on the bottom of the container. It's very minuscule. And so as it dissolves, some of it may go back and undissolve, and then it can dissolve again and go back and undissolve. So it's a constant interplay between basically these two pictures. All right, so let's go ahead and define one more thing here, and we're going to look at our solubility curves. It's and that's what I just passed out to you. Thanks, Frank. So these are your three definitions of saturated, unsaturated, supersaturated. Define them how you want to, and then we're going to look at these graphs. So just make sure that, and you guys have your reading guide still, you may even just be annotating a couple of ideas there, circling, highlighting things there, because you've already done a lot of the work. Work smart, not hard. I graph real quick. I'm sure you're all thinking, like, what actually is a supersaturated solution? It makes sense what an unsaturated solution is. You just haven't put enough in it. But theoretically, you probably should never be able to make a supersaturated solution because you only have so much solvent. It's only going to dissolve so much solute. But what you can do is you artificially make it dissolve more than it should. So when you make it dissolve more than it should, it's super unstable. So you see right there, it says unstable. That's the key part there. You look at it and it'll get so disturbed, it will solidify because it's theoretically holding too much solid. It doesn't want to hold that much. But what I do is I heat it up and I make it dissolve where I want it to dissolve. So you see the solution? It's a liquid, right? Let's assume it is supersaturated because they're very fragile solutions. And my goal is to show you what happens when you disturb it. So, look closely, my dears. So I have a solution, which looks like water. Cross your fingers and squirt. See it? Okay, so I can't turn it upside down because it's actually, it is supersaturated. But there's some water, extra water in there. My lab assistants, we have to like baby it. But feel it as now it's dissolving. I mean, feel it as it solidifies. I was going to turn it upside down for you like Dairy Queen, but there's water. I'm not going to do that to us. So that's our sodium acetate supersaturated solution. You see it does not want to be dissolved. Yeah, as soon as I disturbed it, I just kind of clanked the top of the glass with my magic wand, and it has now precipitated out, is what we call it, or it has desaturated is another way to name it. But you can definitely see it has turned solid, and in that process, you guys that are feeling it, what do you feel? It's warm. It's actually releasing energy as it goes back into its more stable place. Shoot, man, look at that. Okay, so it does not, it didn't want to be in that like kind of high energy, really unstable state. So now that we're putting it back where it's more stable, it's releasing its energy. And this actually is what's in many times hot packs, sodium acetate. Okay, so I didn't warm it up or anything. It's been sitting, I warmed it up yesterday to saturate it, super saturate it, and then I let it sit overnight and didn't look at it. Just kind of like peeked at it this morning, make sure it was still in solution, and I disturbed it, and it was so unstable, it started to precipitate out, and you can definitely see it's warm. All right, so yeah, keep passing it around, Meg. When you get it, just pass it back to the lab station and I'll get from there. All right, so we have this solubility curve, which is supposed to give us information about all of these different solutes, how much do they dissolve, at what temperatures, and so forth. So sodium acetate's not on here, but you can definitely see that some of these are more soluble than others. Who seems to be very, very soluble at most temperatures? Who has the most grams dissolved in 100 grams of water? All right, KCH, okay. Potassium nitrate. Okay, I want you guys to try your nomenclature. You can see that this one becomes very soluble at pretty decently low temperatures. Who's basically not soluble? Who's declining? Say again? Ammonia, okay? So these are actually two really important ones to notice. So potassium nitrate is very soluble. It's going to increase its solubility with increasing temperatures, potassium nitrate. All right, so use that same language for ammonia. Ammonia, NH3, decreases solubility with what? Increasing temperatures. All right, so we see some dichotomies here, but that's very rare. We don't see that very often. What's different about these two substances? Their composition, so this is a what? KNO3, potassium nitrate is an ionic compound. It's a solid at room temperature. It becomes soluble in water, and even more soluble when the water or the solvent is hot. What about ammonia? No, that's ammonium, NH4. This is covalent, so it's what at room temperature? Liquid or gas. This is what cat pee smells like. So don't you smell cat pee? Or it smells like ammonia? When it hits you in the face, it's not a liquid, right? It'd be gross. It's a gas. Okay, so most of the time ammonia exists as a gas at room temperature or many other temperatures as well. So gases are bubbling at the top of the solution. They don't want to stay in solution. They have such high kinetic energy. The high kinetic energy aspect of the gases makes them evaporate out of solution. They don't stay in solution very well. Even at really hot temperatures, even higher kinetic energies, they start to pop out of solution. So there is a difference here because this is a gas and that's a solid. All right, so you can definitely see some information. Oh, for yourself, and this is on your paper, maybe. Here on the line is what kind? So when I say on the line, I don't mean online. I mean, like, let me be specific here. That line I just highlighted, potassium nitrate, that line is the saturated solution line. So on the line means it's saturated. So at 70 degrees Celsius, what is the saturation point, or how much potassium nitrate can be dissolved? That's 70 degrees Celsius. I'm going to highlight this a little bit better. So you're looking where the intersection of those 2 points occur, right? So at 70 degrees Celsius, go all the way up, pass all these other jokers, and get to potassium nitrate. How much dissolves? So it's saturated at 130 grams of potassium nitrate in 100 grams of water. Yeah? Okay. What if I put 150 grams in there at 70 degrees? It would be super saturated. Now that would be assuming that I made it stay in solution. So if I was putting 150 in, I would be up here. So here's the point. If you're on the line, when you do your little finding the point, it's saturated. If I said 150, I'm above the line. So what does above relate to? Super saturated. So what's another way? Above means super, prefix. Superimposed, like on top of. So there's many ways you can maybe think of that. But this is our super saturated solution. And then what if I said, oh, I'm only going to put 80 grams in there at 70 degrees Celsius? That would be what? Unsaturated. So 80 would be down here. Notice that I'm under the line, right? So I could put how much more in to make it saturated? Yeah, from 80 to 130 is, I could add about 50 grams and it would become saturated. If I could slow down the precipitation rate, if I put 150 grams in there, how much would precipitate out to meet saturation? About 20. So 50 to the 130 is 20. So you can read, do you see how to read this graph a little bit more? Okay. So let's look at the questions that are following. These are underneath the solubility curve on your paper here, but according to the graph, you don't have everything you need. So I gotta make sure we're watching the time here. I got 2 minutes. Let's just do 2 of these, okay? According to this graph here, do you guys see KBR? It's the one starts at 60 and goes pretty straight. Potassium bromide, do you see it? Right here. How many grams of potassium bromide, or bromide, I think I said bromate, sorry, will dissolve in 100 milliliters of water at 80 degrees Celsius? What do you do? Go to the 80 and then do what? Trace it up until you see potassium bromide, and then you go over and how much would dissolve? 100 grams and 100 milliliters. It's a nice ratio. It's a 1-to-1 ratio. Okay. Yeah, I think we're good right now. Okay, so we're gonna finish this up on the thing. Here's what I want from you. Not a whole lot. I want you to start. Yes, there's a combined. Yes, it's 15-16. Start it. It's underneath. You have 6 minutes. Yeah, leave these puzzles with me. We're not quite going to make this, but it's okay. You guys do great. A lot of kind of easier concepts for this is going to end on Friday. I know you guys have some CK12 to do. I need to see that you have started every single topic. I know I'm thinking the couple of them with the 3 responses, you're like, I don't know what's sig figs or what's units or what. So I want you to attempt every topic. And if you don't get 100% on all of them, so be it. I want to make sure that you practice them because I don't want to give you a 100 grade test grade. I want you to earn your test grade. Yeah, so it's a combined problem set. It's called 15-16 on your documents. I will also make sure that you're processing through CK12. So we leave in a minute, so put your laptops up, guys.